So now let's have a Python example for the rectangular window. So here I'm using matplotlib to plot and NumPy for mathematical computations, and we're defining a rectangular window with 11 samples from 0 to 10. And here they're 0 when n is smaller than 0 and 0 when n is bigger than 10. So this is just constructing our rectangular window. Now I'm going to use IPy widgets interact just to give some interaction of our plot, and we can change the length of the rectangular window. We are going to use some IPy widgets as just a slider. We are also going to use SciPy signal to compute the frequency response of the rectangular window. And here, this is how we're defining this interact with a slider. And this is the function to plot the frequency response of the rectangular window. So we're defining our rectangular window in the time domain. Then we're calculating with signal frac z. So SciPy signal frac z, we're calculating the frequency response. And here we are having the magnitude of the frequency response in 20 log 10, so it's in dB, and we're finding some maximums values. So we will have here like this, we have the omega at 3 dB, and we have the omega at the first side lobe, so we can have better see this attenuation from omega equals to minus 3 dB and omega at the peak of the side lobe. Then this part here we are using to annotate, so we're creating these arrows and this text. And then we have two plots, one for the magnitude in dB and one for the phase in the degrees. And here we have a slider and just unwrap, so we can see the linear phase easier when using unwrap. So this is our function, it's interact. It's a rectangular window, so it starts with 16, the length of this rectangular window, and we see that if we make the window longer, we see that it's trying to go and become similar to an impulse, but of course we cannot go infinitely long, so we will always have these characteristics. And we see that even this attenuation for the peak of the side lobe, it decreases, but it's not so significant in this case. So we notice that the longer the window, the narrower become the main lobe. And if we go, for example, to a very short window, so let's say 8, then we see that the main lobe and also the side lobes, they become wider, and we have this difference in attenuation here. So we have from minus 3 dB to minus 12 dB, so maybe we have here something like 10 dB, and here how the phase also, it's a linear phase. So this is just a plot, so we can investigate a bit more the rectangular window, and we can see that this is far for bringing an impulse at frequency 0. In fact, it's somewhat broad, and also the attenuation is not very high, so it's in the order of minus 15 to minus 20 dB. We expect that our resulting low-pass filter will inherit these properties through the convolution in the frequency domain. So the pass band, or the main lobe width of our function, will determine the transition bandwidth. So the main lobe width of our function, let's have the main lobe width will determine the transition band of our resulting filter. and the stop band attenuation of the window will determine the resulting stop band attenuation of our filter. So this shows that the window function shapes the key characteristics of our resulting FIR filter.